this video we're going to be going over another stormwater runoff calculation example problem. And in this case, question number 2 here, we've got a park that basically has an area of 2 acres. This is pre-development, and then what we're going to end up doing is we're going to end up adding in a 1/4 of an acre concrete pad to this park area. And so as you can imagine, we're going to have a 1/4 of an acre of the concrete pad, and then we're going to have 1.75 acres remaining of the park. So let's go ahead, let's get ready to begin. Additionally, I do have the equation sheet as well as the official engineering formula sheet up. I also have the TI-84 calculator emulator up as well that I'm going to be using. So they end up telling us that the area at the beginning is 2 acres. We are located in Nashville, Tennessee. A 1/4 of an acre concrete pad will be placed on the lot. Our local regulations require that the post-development runoff be limited to pre-development runoff for a 50-year, 2-hour rainfall. So let's go ahead. Let's put this down. 50-year, 2-hour rainfall. It's going to be important that we know that. Remember, that's going to be how we can determine our CF and also I value. So we're going to write that down. So what we can also end up doing is we can create our little diagram here. So we've got the good old park, right? So maybe we end up creating a little park here, just like we had. We got the little slide, so we could end up creating that. And then maybe right here, right, we've got our little slide for our park. So we got that. So this is Q pre, and then we're going to end up having our development where this becomes concrete right here, and then this is 0.25 acres, right? And this was just initially 2 acres. So that means from this, the remaining 1.75 is going to end up being our park here. So let's go ahead, create a little slide again. There we go. So then 1.75 acres of the park, and then that's going to be the Q post scenario there. Okay, so starting off, let's go ahead, let's calculate out Q pre. Now in Q pre, it is literally just CF CIA for our park. And so what we can end up doing is using the information that we have here, the 50-year, 2-hour rainfall. We can actually go into here, into this runoff equation sheet that basically condenses all of the information that we need. And we can end up finding what that rainfall intensity is going to end up being here. And so as we said, 50-year, 2-hour rainfall. So 50-year, and then we've got 2 hours. I is going to be 1.66. So we can write that down. And this is going to be across the board, right? So I equals, let's go back there and make sure we got the correct one, 1.66. So 1.66, and remember that unit is inches per hour. And so this is going to be across the board. Now also, we can end up looking at our return period. So we can find the CF value. Based off of that, the good old runoff coefficient adjustment factor. And so we have a 50-year storm, so CF is going to be 1.2. And remember, for this entire problem, CF is going to be 1.2 and I is going to be 1.66 because we have a 50-year, 2-hour rainfall in Nashville, Tennessee. So if we end up going through here, we go ahead and start writing things down. So CF is going to be 1.2. C, we're going to have to find that. Remember, that is based off of the surface that we are dealing with. And in this case, it's going to be that park. We also are going to have I here, which, as we said, is 1.66 inches per hour. And then in terms of A, it's our area in acres. We've got 2 acres starting off here. Okay, so let's go ahead, let's find that C value. What we can do in that PLTW engineering formula sheet is just press Control F, and then what we can end up doing is we can actually search for park. So if we put that in, it'll end up bringing us to section 15, stormwater runoff, and we can find the rational method runoff coefficient. Well, for parks, it's 0.1 to 0.25. They do not mention anything about using the lower range or the higher range of this number. So what we can do is just find the average of this. So if you wanted to play it safe, you could end up adding this up. We got 0.35 divided by 2. So we are finding the average here, right? We're finding the average because they did not tell us use the lower range or the upper range. So we're just making an approximation of this, okay? So 0.175 is what we're gonna end up using. So C is 0.175. So now this C value is for the park, right? So whenever we get to Q post, it's gonna be that same C value. However, the concrete will have a different C value then. So now what we can end up doing is just plugging all of these values into our equation, right? So we're gonna find the product of all 4 of these numbers. And so what we can end up doing is we can end up using our good old TI-84. I'm going to actually pop it out of the window or that tab. I'm gonna place it right there. And then let's go ahead, let's do this. So we've got 1.2 times 0.175 times 1.66 times 2. That's going to end up giving us 0.6972. Now, if we want to round to the nearest hundredths place, in this case, this is a 7, so we got to round this number up. We're going to end up with 0.70, and remember that is a unit of cubic feet per second. Q always depicts a flow rate. Whenever we were talking about the heat gain and heat loss, you'll remember we had Q prime, and Q prime equal to AU delta T. The flow rate in that scenario was the amount of heat leaving our home per hour. So in this case, it's a flow rate, right? We're using Q, but in terms of the flow rate for these questions, it's the amount of water that is leaving this property, that is running off of this property, and that is cubic feet per second. So that's the Q pre scenario here for the 2 acres. We're gonna have 0.7. So now what we can do is we can start to dive into the Q post here. So I can just do like a little separation here, and then we can do Q post. Now Q post, a little bit more complicated, just a little bit more. We now have to calculate out the value of the Q of the park, and then also the Q of the concrete. So what I'm gonna do is here is I'm gonna go QP plus QC. And so we have to calculate these out individually. Let's go ahead, let's begin with the Q of the park. So Q of the park is equal to CFCIA. Now, in this case, CF across the board, 1.2 as we said, right? Now C, just as we said, this is for the park. We just found C for the park over here, right? So we can use that same value, 0.175. I remains the same across the board, so it's 1.66 inches per hour. And so remember, I is going to remain the same for this entire problem, right? Because it's a 50-year, 2-hour duration storm in Nashville, Tennessee. So A equals, now this is where our area is going to change. Initially it was 2 acres of park. Well, we're taking off 1/4 of an acre to create a concrete pad on there, right? So we're actually going to have 1.75 acres now. So now what we can end up doing is for this section that is the park, we can end up finding the product of all these numbers, right? CF, C, I, and then A right there. Okay, so let's go ahead and let's punch all these numbers in. 1.2 times 0.175 times 1.66 times 1.75. And so now we have about 0.61 cubic feet per second of water running off of this parkland here whenever it's 1.75 acres. And so now we found QP, right? Now we just got to find QC. So QC, we can go ahead and write down here, is going to be CFCIA. Now CF, it's going to be the same where it's 1.2. C, that is based off of our material type, right? So that is going to be different now that it's concrete that we're dealing with. And then we also have I, that's still remaining the same because we're still talking about that same 50-year, 2-hour rainfall. And then the area here is going to be 1/4 of an acre because our concrete pad is just 1/4 of an acre there. Okay, so what we need to do is we need to find out C for the concrete. So what we can do is go back to our good old handy dandy engineering formula sheet and we can type in concrete. Now, as you can see up here, it has anywhere from 0.8 to 0.95. Now, they do not mention use the upper range. They also do not tell us use the lower range. So what we're going to do is we're going to make an approximation between these two numbers, which is finding the average. And so what I can end up doing is I can bring up the good old TI-84, and we can take 0.8 plus 0.95. 0.8 plus 0.95, which is going to end up giving us 1.75. Divide that by 2 to find the average. Our average value is 0.875 there. Okay, so now that we have all four of these numbers, we can go ahead and plug in these values into this equation. Now keep in mind, this C value is pretty high for the concrete, right? So what we're going to end up finding, despite only 1/4 of an acre being our area, this is going to be a pretty high QC value. So let's go ahead and plug this in. We've got here 1.2 times 0.875. Oops, I'm not typing into there. Let's try this out again. 1.2 times 0.875 times 1.66 times 0.25. Now, whenever we calculate that out, we end up finding that we've got an entire 0. Now, I'm going to end up rounding this to the hundredths place. So we're going to go 2 decimal places out. 0.44 cubic feet per second, leaving for the runoff for that concrete section. And so as you can see, that's a pretty high number, right? So now for Q posts, it is equal to the Q of the park plus the Q of the concrete. So we got to add this 0.61 and 0.44. So let's go ahead and do that. 0.44 plus, oops, almost I put in there. Let's do this, delete, yep, plus 0.61. Now we can put enter in here, and what we end up getting for this Q post is that it is 1.05 cubic feet per second. And so that's what our Q post value is. Our Q initial value was 0.7, and so now what we've got to do is we've got to subtract these two numbers, and so we can find delta Q. So delta Q is just the change in Q, and so remember, change in, or delta, is always the final minus initial. So we got Q post minus Q pre, and so now if we end up punching this in, we got 1.05 cubic feet per second minus 0.70 cubic feet per second. And so now we can end up performing this calculation. I already have 1.05 in there, so we can subtract 0.7 on here. And so now we're going to end up with 0.35 cubic feet per second, right? And so just as we were talking about in class, delta Q should be equal to 0. Now this value, you might see this, you might be like, oh, it's not all that bad, but we still would have to take this into consideration. We want to try to get this number to be as close to 0 as possible. And so we were talking about in class some things that we could end up doing for this. In terms of that stormwater management plan, we would want to end up creating a stormwater management plan, and that could consist of, maybe in this park, we end up adding in a retention pond. Maybe we add in a detention pond. Maybe we end up changing some of the slope and the topography of this land to help out so that not as much water will run off. Maybe we end up having a water collection basin so that we can end up storing some of the rainfall, and then we can later use that, right? Maybe they have like a garden in the park. Then if they end up storing that water, they could reuse that water to be able to water the garden. All of these different options we can end up implementing so that basically we can try to get delta Q down to 0. And another option too, just to give you guys a copious amount of options, is we could also add in extra vegetation too, right? Extra vegetation, especially for an area like a park, would be pretty great, and that'll bring this delta Q value down as well. Anyways, hope that was helpful. Thank you all so much for watching. Catch y'all in the next video. Bye-bye.